Sir, your video is also seen, PPT and video.
Hello?
Yes, sir. I can see your video and audio.
Okay,
PPT, it
sir.
was visible.
Okay, sir.
Now I
I'll
think, okay, you can share. Sir,
read
Ravikumar, sir, you can turn off video. That will save bandwidth.
done, sir. Done, done.
Yes, yes, sir. Uh, for,
Is it okay, sir, now?
yeah. Uh,
Are you able to see the screen?
no, sir. Screen is not visible.
Okay. It's funny. Now, sir?
No, sir. Yeah, yes, yes, sir. Now we can see.
Okay, sir.
Now
Can I
we
go
can see.
ahead?
Sir, I'll start the session by introducing. Dear participants, it is my privilege to introduce Mr. J. Ravikumar. J. Ravikumar obtained his graduation from Bangalore University, PG diploma from Germany, and he has a vast industry experience of 30 years. As a branch in charge for microwave division and IED division for 10 years with the Scientific Instrument Company Limited, SICO. Presently, he is the chief executive of Technilab Instruments for 20 years. More than 25 years, he is involved in manufacture of microstrip and microwave devices for industries and educational institutions. His company is authorized channel partner for Rode and Short for Germany. He's involved in indigenization of microwave components for high frequency transceiver module of flycatcher radar, component for weapon locating radar, Trishul and Akash missile for Bharat Electronics Limited. Ravi Kumar sir had undergone training at Sartoris, Germany, installed nanocalorimeter for Baba Atomic Research Center, BARC, Mumbai. He's involved in establishment of Center of Excellence Avionics, the project funded by the Government of India for Manipal University, and he has supplied various technical equipments like flight controlled modules, high resolution long distance IR camera. Currently, Mr. Ravi Kumar is working on electronics workbench for IAF radar section, Bangalore, and he has also successfully developed HPBW adapter for IAF BRD-7 flight aircraft. With this introduction, it is our it's a very great opportunity for all of us to learn from Ravi Kumar sir, his industry expert and industry experience. So I thank you, Ravi Kumar sir, for accepting our invitation and presenting this talk today. Thank you.
Thank you very much, sir.
Kumar sir, now we can start. Yeah.
Thank you, 2Session, sir, for giving this opportunity. And also, I thank all the participants for having attending this program. So let me start with a very good afternoon to all the participants. So today we will discuss about the fundamentals of antennas. So Technilab instrument has been incorporated in 2004 with a vast experience of experienced personals from industry and research institutions. And we are engaged in design, manufacture, and distribute test and measuring instruments for RF and microwave domain industries and institutions. We are being an OEM, we offer high quality products and reputable service, which has an edge over our competitors. Our products are widely used in institutions and universities, commercial, industrial, military applications, including cellular, wireless, aerospace, satellite, broadband, RFID, and many more. Currently, we are actively working on 5G in association with our principals, Mrs. Rode and Schwartz, Germany. Today, we'll talk about the basics of antennas. So in this session, we will discuss the basic functionality of antennas, starting with Hertz antenna model, followed by a short introduction to the fundamentals of wave propagation the important general characteristics of an antenna and its associated parameters are explained. A more detailed explanation of the functionality of some selected special type of antennas. So with this, I'll go to the next slide. So what is an basic function of an antenna? Antenna acts as a converter between conducted waves and electromagnetic waves propagating freely in space. Their antenna name is borrowed from zoology, in which the Latin word antennae is used to describe the long, thin feelers possessed by many insects. I repeat, antenna acts as converters between conducted waves and electromagnetic waves propagating freely in space. So what is an antenna? An antenna is also called as an aerial. An antenna is a conductor that can transmit or send and receive signals such as microwave, radio, or satellite signals. An antenna is a transducer which converts electrical power into electromagnetic waves and vice versa. The sole functionality of an antenna is power radiation or power reception. Antennas are in general passive devices except some smart antennas which has certain electronic devices for beam scanning, etc. So wherever there is need for wireless communication, there occurs the necessity of an antenna. Without antenna, there is no communication system, and antenna plays a very vital role in the radio link. So let us discuss about basic antenna functionality. So antenna is a device which helps to propagate or radiate waves in space. Like, to have a transmitter with help of a conductive wave or through a RF cable, the signal is fed to the antenna. The antenna radiates both electrical and magnetic field into free space, which is radiated wave propagated in free space. So this is a basic functionality. The antenna acts as a transmitter and also acts as a receiver. Any antenna, a transmitting antenna is one which converts electrical signals into electromagnetic waves and radiates them. Similarly, a receiving antenna is one which receives the beam of electromagnetic waves and converts it into electrical signals. An antenna can be used either as a transmitting antenna or a receiving antenna. The basic functionality is antenna is used either to transmit signals or to receive signals. So basically there are two types of antennas which were originally designed. One is the monopole antenna, other is a dipole antenna, or it is called as Marconi antenna or Heinrich Hertz antenna. The oldest existing antenna, such as those used by Heinrich Hertz in 1888 during his first experiment to prove the existence of electromagnetic waves, were in theory and in practice not so very different from an RF generator. I repeat, the oldest and the first model of existing antenna of Heinrich Hertz developed in 1888. So this is the figure where you can see this is the first Heinrich Hertz antenna module, where you can see there is a two conducting plates. The charge is fed to that. similarly acts as an inductive load as well as transmitting energy. So I'll explain in detail about the figure. An antenna can be derived from a parallel circuit which consists of an inductor and a capacitor. If the plates of the capacitors are bent open and the inductor is reduced to the inductance of the wire itself, one ends up with a dipole antenna as shown at the above figure. In fact, the resonant circuits are still frequently used even today as a means of explaining the individual properties of antennas. It was not until around 1900 or even later, when transmitting and receiving antennas were being built, that a clear distinction was made and antennas were classified as separate components of radio system. So this is an important slide where you can see the complete radio link. And here in this particular slide, you can see there is a transmitter, there is a receiver, and there is a transmitting antenna, there is a receiving antenna. In between, there is a propagation path, or we call it as free space. And here it can be seen that the antenna plays an important element in any radio system because it acts like a link of a chain. So the overall performance is significantly influenced by the performance of transmitting and receiving antenna. And also very important aspect is your receiver sensitivity. The receiver sensitivity can be minus 10 dB, minus 20 dB. It can go up to minus 170 or 180 dB. The highest the sensitivity of your receiver, the reception of your system is excellent. So this forms your complete radio link where you have four important devices, that is transmitting antenna and a receiving antenna along with the transmitter and receiver. So let us talk about the far field conditions. What is a far field conditions? So you have to keep certain criteria in mind before we place the antenna. That is the distance between transmitter and the receiver. The distance from an antenna where far field conditions are met depends on the dimension of the antenna with respect to the wavelength. For example, for smaller antennas, that is half wave dipole, the wavefronts radiated from the antenna almost become parallel at much closer compared to electrically large antennas. A good approximation for small antennas is that far field conditions are reached that is greater than 2. A simple example, as soon as the antenna radiates a signal, it is a curved wave. After certain distance, it becomes plane wave, and any measurements are made at plane wave condition, the results are good. So this minimum far field conditions has to be maintained for any antenna measurements. So here is an image where we have showed that far field condition formula 2d square by lambda, where S is the distance between a transmitter and a receiver, and lambda is the wavelength of the frequency at which your signal is getting transmitted or received. So for large antennas with a larger aperture, the distance will be far. Antenna with a very small aperture, the distance will be less as per the calculations. That is this formula 2d square by lambda. So this particular image will really take you to show that how your radiation pattern of an dipole antenna depends on the length of your dipole. Suppose you design an antenna, dipole antenna, where the element is lambda by 2, you get a perfect figure of 8 radiation. If I remember yesterday, Dr. Puneet Mishra, Isaac Ahmedabad, was insisting the necessity for type of radiation required. In one of the slides, he has shown that the radiations are almost like the shape of our Indian map, because they want to focus the energy particularly to the population of our country. So they designed antenna with radiation pattern which will suffice the requirement of our population. Similarly, here you have, when you vary the lambda by dipole length by 1 lambda, the radiation pattern varies. Similarly, when you increase the length of the dipole by 4 by 3 lambda, you get a different type of radiation pattern. Similarly, you can go for 3 by 2 lambda or 2 lambda. Same conducting a radiating element radiates different type or different fashion once you are not meeting the lambda by 2 conditions for a dipole antenna. And here also we call as wavelength ratio for the performance of the antenna. So here, this is one image where you can see this is the ideal free space condition, or we call it as Fresnel ellipsoid. Here you can see the terrain is not smooth, it's a hilly terrain, but still you want to radiate the signal without any much losses. So they have mounted 2 antennas on the tower. You can see in between there is a free space, and there should not be any obstructions in between. This condition, we call it as free space condition. And here free space condition requires a direct line of sight between the 2 antennas involved. That is between a transmitter and a receiver. Consequently, no obstacles must reach into the path between them. Furthermore, in order to avoid the majority of effects caused by superposition of direct and reflected signals, it is necessary that the first Fresnel ellipsoid is completely free of obstacles. In the earlier days, when we switch on the television, maybe 20 years back, you will see the ghost image. The ghost image is only because of superpositioning of the reflected signals, or there is a delay from the signal which is directly from the transmitter to the receiver, and there is a reflected signal coming from the nearby obstacles. So this we call it as a superposition, and that has to be taken care in the first Fresnel ellipsoid to avoid superpositioning or ghost image or echoing in case of audio signal. So let us talk about polarization. There are 3 types of polarization. One is vertical polarization, and other one is circular polarization, and other one is elliptical polarization. So in the image you can see the pointing E vector. E vector varies depending on the polarization. See, the polarization of an antenna is determined by the direction of the E field. A distinction must be made between following type of polarizations. One is linear polarization, where E field vector changes in magnitude only. In case of circular polarization, the magnitude of the E field vector is constant, but the direction changes and rotates around the direction of propagation. In elliptical polarization, the magnitude of the direction of the E field vector changes, and its peak position can be described by an elliptical equation. Apart from the basic three polarization, that is linear polarization, circular polarization, elliptical polarization, there is also cross polarization, because certain satellites which transmit signal may be circularly right hand polarization or circularly left hand polarization, or there is chances that if polarization is not taken care, you may get interrupted by the signals from the other satellites which are coming in the similar direction. So polarization plays a very, very vital role in case of antennas, more importantly for space communications. Am I audible? Is there any questions till now?
Ravi sir,
Yes, sir.
sir, some participants are unable to clearly view the slides. Can you start the PPT slideshow?
Okay. Should I go back?
No, at the bottom we have, we can start the slideshow so that it covers the whole screen.
Okay. Okay. Vinay, sir. Just a minute, sir. Yeah. This slide, I think it's clear, if I'm
Yeah,
right.
it's clear, sir, but there were some images and block diagrams. So the participants have requested on the chat box.
Okay. 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 Okay, sir. I'll take care of that. The full image file ಅಂತ. ಇಲ್ಲ
You can start the slideshow. At the bottom, you have options.
ಸ್ಲೈಡ್ ಶೋ ಎಲ್ಲಿದೆ?
Yes, sir. Yes, sir. Now you can just go ahead to your current slide.
Okay, okay, sir. Yeah, this clear, sir, now?
Yes, sir.
Thank you. Let us talk about the general characteristics which decides an antenna, or general characteristics of an antenna, or a performance of an antenna. Here we have the major one is the radiation density, radiation pattern, directivity, gain. There is a practical gain, effective area, input impedance, nominal impedance, impedance matching, and voltage standing wave ratio, and bandwidth of an antenna. So you take any type of antenna, they have to fulfill all these criteria for optimum performance or the best reception or the highest sensitivity of an receiver. So let us talk about what is radiation density. Radiation density is the simplest imaginable antenna, is an isotropic antenna or a monopole antenna, but makes an excellent theoretical model. An isotropic radiator generates wave with spherical wavefronts that are radiated uniformly in all directions. When the ideally matched transmitter power PS is applied to it, then at distance r, this gives rise to the radiation density. That means radiation density is maximum power available at a certain distance when the energy is completely transmitted from an antenna with very less antenna resistivity. We are taking an example of a monopole antenna, which is an isotropic radiator, which radiates energy in all 360-degree. When you are seeing in a 3D image, you can see it like a donut, where the maximum energy is at a certain distance r. So this is very important because the basic idea is to transmit maximum energy with very less antenna resistivity or dielectric resistivity, etc., depending on the material on which the antenna is fabricated. So this is about the radiation density. Let us talk about a very important parameter, that is radiation pattern. How is your antenna transmitting the signal from the antenna surface, or whether it is a end-fire antenna or a broadside radiation antenna? So the three-dimensional radiation behavior of antenna is described by their radiation pattern, normally in the far field region. The three-dimensional radiation, that is XYZ axis, how the energy is getting radiated in all the three dimensions in a far field condition. As explained before, only an isotropic radiator would exhibit the same radiation in every spatial direction. But this radiator cannot be implemented for any specified polarization and is therefore mainly suitable as a model and comparison standards. Dipoles and monopoles possesses directivity. An electrically short dipole in free space has a three-dimensional radiation pattern as shown in one of the above figure, with nulls in the direction of the antenna axis. The radiation pattern determines which direction the maximum energy is transmitted from the transmitting antenna. Similarly, the receiving antenna also. So here I am showing you one polar pattern. This is called as a radiation pattern of a dipole antenna, where the vertical pattern of a dipole antenna is shown in the image. You can see exactly there is a figure of 8. In case it is for a perfectly matched antenna with very less VSWR. So this is one of the radiation pattern of a dipole antenna. Similarly, we can have a look at the radiation pattern of other antennas too. So what you have seen is a polar. Here this is the Cartesian plot, where you can see the main lobe, which has the maximum energy that determines the directivity, followed by side lobes. On the right side, you can see there are 3 side lobes. Similarly, left side, less. That may be due to the reflections coming from the surroundings if the antenna is not placed in an anechoic chamber. And also you can see some null points. And this is about the Cartesian plot, same for the dipole antenna. So from the radiation pattern, the following additional parameters can be derived. The side lobe suppression or side lobe level is a measure of the relation between main lobe and the highest side lobe. The side lobe suppression is a measure of the relation between main lobe and highest side lobe. The next is your HPBW, which is half power beamwidth. Half power beamwidth is the angle between 2 points in the main lobe of an antenna pattern that are down from the maximum by 3 dB. It is nothing but half power. It is usually defined for both principal plane patterns. And the front to back ratio specifies the level of radiation from the back of a directional antenna. It is the ratio of the peak gain in forward direction to the gain in the reverse 180 degree direction. It is usually expressed in decibel. See, this image very clearly shows half power beamwidth region, and also it shows 3 dB power level. The first dotted line shows the power is 0 dB, that is maximum power. The second dotted line, curved line, shows the power is reduced by half when the antenna is moved from the line of sight. The antenna is moved on both sides from the line of sight so that you can see where the energy is fallen by half You can make a note of the degree angle, and you can specify whether at a 60 degree either side your energy is down by half. That again determines what type of antenna is used, whether it is a Yagi antenna or a dipole antenna or a patch antenna. Antenna can be anything. The 3 dB is nothing but half power beam width. And you can see side lobes and back lobes and also one null point. Here in the first main lobe, you can see the maximum energy or electrical signals are present. So this is one of the pattern generated by Yagi antenna. So next very important is the directivity. How good is your antenna able to deliver energy in the forward direction? That is, the directivity factor D is defined as the ratio of the radiation intensity obtained in the main direction of radiation to the radiation intensity that would be generated by loss-free isotropic radiator with the same radiated power. The radiation intensity can be replaced by power density represented by pointing vector as shown below. See, basically the directivity very clearly tells what is the maximum energy which is radiated or transmitted from a transmitting antenna in the forward direction. So the maximum distance it can cover can give a better directivity. And we have with S perpendicular to E and S perpendicular to H, E perpendicular to H in the far field, the power density is measured at the same distance R from the antenna. The following are the formulas where people apply to measure the energy or the directivity of the particular given antenna. Field intensity can also be measured by power transmitted divided by 4 pi. So similarly, we have one other important is the gain, or we can also call it as a sensitivity, receiver sensitivity, or your antenna gain. So corresponding to the directivity factor, how good is your antenna's directivity? Correspondingly, the gain also will be good. The gain is the ratio of the radiation intensity obtained in the main direction of the radiation to the radiation intensity that would be generated by a loss-free isotropic radiator with the same input power PT. PT is power transmitted or the input power to the antenna. With the formula, you can find out gain. You have multiple, we have other equations also where gain can be calculated. You can also take 4 pi s by lambda into square root of power received divided by power transmitted. So we have multiple formulas can be used for calculating gain of the antenna. So here we have, in contrast to the directivity factor, antenna efficiency is taken into account in the above equation. In the following applies. Gain equal to antenna efficiency into directivity. Similarly, for example, if your antenna with efficiency 100%, that means the gain and directivity are equal. In practice, this is hardly the case. So the gain, which can be easily determined during measurement, is the parameter which is more frequently used. Suppose your antenna directivity is good, your gain also is very good. So we have another formula where gain and directivity are often expressed in logarithmic form as mentioned below. And also, contrary to common rules and standards, it is well established practice to indicate reference with an additional letter after dB. So what we can call dB? dB is nothing but decibel. dBi refers to decibel isotropic. or dBi refers to isotopic radiator. dBd refers to decibel half wave dipole. dBm, that is decibel per milliwatt. 0 dBm in reference to 1 milliwatt. Similarly, we have dBc. Decibel relates to carrier, that is the power ratio of a signal to the carrier, that is dBc. dBm is logarithmic and milliwatt is linear. So these are all the units which are used to measure gain of an antenna, like dB, dBi, dBd, dBc, dBm. So we have another important thing is practical gain. The ideal gain is something where there is no loss. Everything is 100% clear. There is one more factor which is called practical gain. While the gain definition assumes ideal matching between antenna and the connected cable and receiver or transmitter. In practice, this is rarely the case. So what is measured in a non-ideally matched setup is called the practical gain of an antenna. Here, any antenna needs some sort of conducted wave to be fed to the transmitting antenna or a receiving antenna, which has its own VSWR value. So there is some sort of losses in the connecting cable and also some sort of reflections in the receiver or a transmitter, and that has to be taken care. So generally, no devices will have 100% 1D losses will be zero like that, VSWR 1. So it has to be applied. There are formulas to measure the practical gain of an antenna. So the gain can be calculated from the practical gain with the following formula. Gain equal to gain of the practical antenna divided by 1 minus reflection coefficient square, where the amount of mismatch is expressed by the magnitude of the reflection coefficient R. So this formula will help us to know exactly what is the practical gain. For that, we need to measure reflection coefficient, or we should know the VSWR of the antenna. After measuring the VSWR, you can obtain reflection coefficient, that is VSWR minus 1 divided by VSWR plus 1. That will give the reflection coefficient. That value you can apply for R. You can arrive practical gain of an antenna. So what is the effective area? We radiate certain power or we feed some power to the antenna. So how effectively it will cover the area of transmission, or how effectively the signal will reach the population where you need to feed the signal. The effective area of an antenna is a parameter specially defined for receiving antennas. It is a measure for the maximum received power that an antenna can pick up from a plane wave of the power density. As in the previous slides, I told very clearly, whenever any signal is transmitted from a transmitting antenna, it is a curved wave. After certain distance, the curved wave becomes plane wave. So your field intensity is present all over. The area the receiving antenna should be able to receive the plane waves, or the antenna that can pick up from a plane wave of the power density. So that formula is represented PR max equal to S into effective area. S is nothing but power density. So here, the earlier slide is continuation of the effective area. Although the effective area of an antenna can be well conceived as a real area perpendicular to the direction of propagation of the incident wave, it is not necessarily identical with the geometrical area of the antenna. The relationship between effective and geometrical area is described by the aperture efficiency. Aperture efficiency is nothing but aperture of the receiving antenna or aperture of the transmitting antenna. So aperture of the receiving antenna is large. That means it can pick up the signal effectively. So this plays a very important role. The antenna aperture has to be designed in such a way it is able to pick up the signals. So let us talk about a very important parameter, the impedance matching. Why impedance matching is important? Because in any transmission system, there will be a source and there will be a load. And people are more interested in maximum power transfer from source to the load. Suppose impedance is not matched, it will give higher VSWR, which is return losses are more. So one of the most significant parameter of an antenna is its input impedance. This is the impedance present at the antenna feed point. Its real part can be split up into radiation resistance and loss resistance. So when you take an antenna system, suppose like a patch antenna, transformer feed patch antenna, you will have three type of transmitting lines present in that. One will be your 50 ohm transmission line. A radiating patch will be of a higher impedance, maybe 377 ohms. To match the 50 ohm line and 377 ohm, you need to have a feed line which is lambda by 4 distance. The thickness of the line is calculated accordingly so that your maximum energy is transferred from 50 ohm feed line to the patch element, which is a higher impedance. So impedance matching is very important in any circuit or even on a printed circuit board design or a patch antenna or any type of antennas. It should be noted that the radiation resistance being the quotient of the radiated power and the square of the RMS value of the antenna current is spatially dependent. This applies also to the antenna current itself. Consequently, when specifying the radiation resistance, its location on the antenna needs to be indicated. So this we call it as an input impedance. And next is quite commonly the antenna feed point is specified and equally often the current maximum, the 2 points coincide for some but no means of all type of antennas. So this is a continuation of the input impedance. The imaginary part X of the input impedance disappears if the antenna is operated at resonance. That means the maximum energy can be transmitted. Electrically, very short linear antennas have capacitive impedance values less than 0, whereas electrically two long linear antennas can be recognized by their inductive imaginary part. So what is a nominal impedance? The nominal impedance is nothing but 50 ohm impedance. The nominal impedance Zn is a mere reference quantity. It is commonly specified as the characteristic impedance of the antenna cable to which the antenna impedance must be matched. As a rule, normalized impedance is 50 ohms. So the very important here is impedance matching and VSWR. So generally it happens, impedance matching yields low VSWR or maximum power transfer from source to load. If the impedance of an antenna is not equal to the impedance of the cable and or impedance of the transmitter, a certain discontinuity occurs or certain reflections take place. So here, if the impedance of an antenna is not matched or equal to the impedance of the cable, there is an uncertainty that your maximum energy will not reach the load. The effect of this discontinuity is best described for the transmitter case, where a part of the power is reflected and consequently does not reach the antenna. However, the same will happen with the received power from the antenna that does not fully reach the receiver due to mismatch caused by the same discontinuity. However good may be your antenna, suppose the impedance is not matched, it may not radiate the desired energy, or it may not perform to the value it is designed to give certain gain. So it will also increase VSWR in the system if impedance is not matched. So here, for example, we have a slide which shows there is a total power we are feeding to the transmitter. There is some power is reflected back and some power is passed in the forward direction. And there is a discontinuity happening because of reflections or due to mismatch. The ratio you can take, ratio of the forward power divided by reflected power will give VSWR of your system. That means maximum energy is not getting transmitted in the forward direction. There is a mismatch. Mismatch is getting reflected back. The mismatch can be due to connectors, can be due to cables, due to waveguides, or in the radio link, there is some component which is having more VSWR, is not allowing the energy to go in the forward direction. Part of the energy is reflected back to the source. And in this particular slide, it's very clear. Suppose you are impedance matching, and this is correlating about what will be the effect if your impedance is not matched properly. See, for a VSWR value of 1.002, your reflected power is almost nil. That means maximum energy is going from the source to the load. Suppose your VSWR increases, your reflection coefficient also increases. See, reflection coefficient for VSWR 1.002 is 0.001. That means minus 60 dB is the power which is coming back. That is very, very low power. So as we know the dB value, 3 dB is nothing but half power, 6 dB is 1/4, 10 dB is 1/10, 100 dB is 100, 20 dB is 100, 30 dB is 1000. Like that you can take 60. That means 1 divided by 10 followed 1 followed by 6 zeros. So very, very, very little power will get reflected back, provided you have a very good VSWR. Suppose if your VSWR is 1.1 and your reflection coefficient is 0.05, there is a chances your power is attenuated, minus 26 dB loss will be there. There is a reflected power is almost 0.2% of your original power. So higher the VSWR, suppose you have a system has a VSWR of 5, that means your 44.4% of your energy is reflected back to the source. That means your system has a very high VSWR and your performance is reduced by half if your VSWR is more. So VSWR of a complete system is calculated between each and every component or a device which goes into the system. That is called as a system VSWR, overall system. One system may have 40 to 50 devices or components to form a system. Say like you have a transceiver. Transceiver will have 40 to 50 devices. Each and every device will have its own VSWR. So they all will get collectively to give a system VSWR. If system VSWR is very low, performance of your system is very high, very good. Suppose VSWR is more, performance will be very less. For example, if you take a radar which is supposed to transmit energy up to 15 kilometers to detect any flying object. VSWR is more. The signal may not reach 15 kilometers. It may reach maximum 10 kilometers or maximum 12 kilometers. So you can't detect the flight which is flying at a height of 15 kilometers if your system has a high VSWR. So VSWR is a very, very, very important parameter in a communication system. So let us talk about the bandwidth of an antenna. What is the bandwidth of an antenna? The bandwidth of an antenna is defined as the range of usable frequencies within which the performance of the antenna with respect to some characteristic conforms to a specified standard. Suppose I have an antenna with a bandwidth of 200 megahertz. So I design an antenna at a center frequency of 2.5 gigahertz. If my bandwidth is 200 megahertz, that means I can operate the antenna from 2.4 to 2.6 gigahertz. So this is called it as the bandwidth of an antenna, or the antenna which can work at an optimal performance in a particular bandwidth. See, the parameter most commonly taken into account here is impedance matching. Once again, we come back to impedance matching, that is VSWR, like less than 1.5, but other parameters like gain or side lobe suppression may serve as a bandwidth criteria here too. Bandwidth of an antenna for broadband antennas, the ratio of the highest and lowest usable frequency is determined. The ratio of 2.2:1 is called an octave, and 10:1 is called a decade. That is, bandwidth is frequency high divided by frequency low. Suppose your frequency high is 2.6, frequency low is 2.4, then your bandwidth will be BW equal to FH minus FL, that is 200 megahertz. If you have a 2.5 gigahertz antenna with 200 megahertz bandwidth. So you can also use this formula where FH is the highest usable frequency and FL is the lowest usable frequency. An antenna is said to be broadband when BW is equal or greater than 2. So here we have another type of formulas. There also exists a different definition of bandwidth, which is valid only for narrowband antennas. A narrowband antenna can be down to 10 megahertz, 1 megahertz, 500 hertz, can be anything, depends on the application where it is used. We have the formula bandwidth in percentage, frequency high divided by frequency low divided by center frequency into 100. This will give the percentage of bandwidth, where FC is the center frequency. Value here can range from 0 to 200% in practice. This definition is used only up to 100%. So bandwidth plays a major role in any communication system designed for certain applications. So let me show some of the antennas what we have designed in our lab. This left side image you can see is a metamaterial antenna, which is nothing but an insert feed patch antenna with the two concentric rings. In between there is a gap. And the similar antenna, the back side of the antenna, you can see there is a two slots. That is, slots are made to increase the gain of the antenna. This is a metamaterial antenna which is made out of FR4 substrate. with a dielectric constant of 4.3 and height of the substrate is 1.6. And you can see below there is a 50 ohm impedance line, and we have connected a SMA female connector which can support up to 18 gigahertz. The frequency, the size of the connector is 2.92 mm female connector. And the radiating patch, which is the copper, is now coated with some material like a tin oxide, or you can go for gold coating depending on the users. And the ground plane is soldered at the back. So let me show about some type of antennas which may be of interest to some of the participants. When they are designing the antenna, like earlier speaker madam was telling how to design, you will get an idea what type of designs can be fabricated. So this is another type of antenna which is made out of FR4, and here you can see there is a defective ground plane at the back side. This all is done to increase the bandwidth and also gain. And people get different ideas for different applications. Some people are designing dual frequency antennas. Some people are doing pentaquad antennas, one antenna working for 5 frequencies. Some people are designing for tri-band, dual band, 4-band, 5-band, like that. So this is another type of antenna where it is a rhombus structure with a EBG on the radiating patch side. Similarly, the ground plane is made defective. So each and every antenna behaves differently. Although the substrate is same, height is same, dielectric constant is same, the connectors used to solder is same, but the performance is different. And the size is very small. It is 1 centimeter by 1 centimeter antenna. Although the image looks bigger, but size is very small. This is fabricated in our facility in Bangalore. So here we have one more type, that is again an insert patch with the ground, defective ground. And the defective ground, you can see there are slots are different sizes. We have made 3 slots. 3 are different in length as well as thickness. So again we have this a loop antenna with a different type of slot sections. You will be seeing there are slots made at different edges. Again, it is for a certain application. And this is a simple one with U slot patch antenna. So like that, we have designed more than 200 to 300 types of antennas. Some are for commercial applications, some are for academics, some are for PhD scholars, some are for our own use to supply to institutions. So this is only an example what we have displayed here. We have quite a good number of array antennas, 2x2, 2x8, and up to higher frequencies down up to 20 gigahertz we have designed. From 900, 800 megahertz to we have done up to 20 gigahertz. So let us talk about the instruments what are generally used for antenna measurements. So here what we are showing is a vector network analyzer, and this is from our principals Rode and Schwartz. This is a 4-port vector network analyzer, which we call it as ZVA40, or we have other model ZVA67, and this particular model can go from 10 megahertz to 40 gigahertz, and this can be expanded up to 110 gigahertz with a frequency multiplier. Basically, these type of instruments are used for measuring return loss, VSWR, impedance, and also you can do a lot of antenna characterizations can be done. Apart from that, you can go for any 4-port, 8-port, 2-port devices that need to be characterized. Like you have couplers which have a 4-port, or suppose you have a power splitters, power combiners 1:8. So all microwave devices can be checked for their VSWRs, reflection coefficient, impedance, Smith charts, everything can be done. These are all the high-end instruments which are generally used by defense, uh, some good institutions who can afford. This approximately cost ranges from 3 lakhs to 80 lakhs. These high-end instruments for which we are the authorized dealers for education in Karnataka. We can offer a good discount for educational institutions if somebody is interested, or you can visit Rode and Schwartz YouTube channel and you can have a video of all these instruments. Of late, these instruments are mostly used for 5G applications, 5G testing, and all those things. So this we have another smaller instrument. This is a two-port vector network analyzer with spectrum analyzer capability, and also you can do a lot of functions which are all associated with antenna measurements. So this is a 13 gigahertz VNA. Earlier I showed 40 gigahertz, expandable up to 110. This is up to 13.6. Now they have come out with another 26 gigahertz VNA also. So with VNA is a very, very important instrument for antenna measurements or antenna characterizations. And we have another instrument. This is a spectrum analyzer with a VNA option. This is a single port device where you can see the spectrum of your received signal. You can also measure the channel power, and also you can measure the side lobes, side bands. All these measurements can be done. You have a tracking generator, and also you can measure the power level of your received signal, a CW signal. And in the higher end models, you have a lot of built-in modulations. QAM can be done, ASK, FSK, QPSK. You can select your carrier wave frequency, and also you can select your modulated signal, type of modulated signal, and also the power level of your modulated signal, as well as power level of your carrier signal, and what type of modulation also you can do. So a lot of analysis, RF measurements can be done with these type of high-end instruments, which is really used in the industries. And here we have one 6 gigahertz VNA, and this guy is using along with a RF teaching board, where the particular board has got VCO, board has got power dividers, board has got some filters. So all RF related parameters can be measured with one single board. There are multiple outputs are available. So you can take whatever output you needed. Suppose you can also take some microwave signals and feed to the VNA. You can see there is a Smith chart where you can measure the impedance at different frequency. You can measure the impedance of the device under test. So a lot of options, a lot of features, everything is software driven. It's available with a one finger touch. You can perform your experiments. You can also do your cable losses. You can also check your device performance. And these are sub 6 gigahertz where most of the RF activities are going on. Up to 500, you can go for CDMA, GSM. And above 500, you can go all this Wi-Fi, Bluetooth, Zigbee. FR1 maybe frequency range 1 in 5G can be tested with a 6 gigahertz VNA. This is another image about the same equipment where every values is displayed and you have multiple markers available on the instrument. So you can select and you can do everything. And this is what the industry does. All Wi-Fi wireless companies. And this is a testing board. We call it as a teaching kit. And also you have with a spectrum analyzer, you have a signal generator, you have a vector signal generator. So all sort of signals can be generated on the table, can be analyzed on the table. Everything can be done. And this is an anechoic chamber, which we have established in some institutions. And again, we make these ultra wideband antennas which work from 1 gigahertz to 40 gigahertz, or 1 gigahertz to 26 gigahertz, 1 gigahertz to 18 gigahertz. That is used as a transmitter, and your test antenna will be the receiver. The receiver is connected to your VNA, and transmitter is also connected to the VNA, where the signal is fed. The known power level signal is fed to the transmitter, and at a certain distance, keeping that 2D square by lambda criteria, your receiver antenna is moved front and back. And this is an image of an anechoic chamber, where even the light what is mounted inside is EM free, electromagnetic waves free, and completely it is isolated up to minus 90 dB, where no signal can come from outside, or whatever signal is transmitted inside the chamber is absorbed by the absorbers. They are all called as polythene or polypropyl absorbers are there. Now some latest materials have come, polystyrene absorbers are there, which has a better life. And these absorbers can go for 10 years. After that, they need to be replaced. And this is a minus 90 dB chamber with a length of 7.5 meters by 3.5 meters. So this particular distance you get around 7 meters, that is 20 feet, where most of the wavelengths, different type of antennas can be used. Depending on the wavelength, higher the frequency they have, the smaller the wavelength. High frequency antennas can be kept close by. Low frequency antenna has to be apart, so that the signal at least have one wavelength or two wavelength, so that your plane wave reaches your receiver. That is about the anechoic chamber, and this is one of the image of the anechoic chamber, where you have the automatic pattern plotting software from the receiving antenna. You can make the pattern plots. So these type of infrastructures are there in ISRO, Indian Air Force, BL, so Indian Institute of Science, IITs, some major institutions have set up. Recently, MS Ramaiah Institute has done, RV College, Christ University. So many people are slowly coming up to establish their own RF Center of Excellence, and we are supporting them, their particular establishments. I will show you about some type of radars which are mounted and which are practically used. These are all the products of Bharat Electronics, where you can see there is a 3D surveillance radar. They name it as Rohini. The top portion is your antenna. Maybe it's a array antenna, phased array antennas are mounted. And this is in the field. And next one is your BFSR radar. This is a battlefield surveillance radar, which is generally called as a soldier mounted radar, which is very lightweight. That antenna is there on the top. This is a cut parabolic antenna is mounted. This is for a short range antenna with a tripod, where they can easily set up this antenna anywhere to detect the movements of personals or any armored vehicles like that. So again, this is a BFSR, battlefield surveillance radar, which is having a different type of antenna which is mounted on top of it, and all the electronic instrumentations are inside the nearby control vehicle, or sometimes it is mounted below that in the same truck. And again, this is an image of an BFSR radar on the front side. And these are all high altitude, low weight radars. They call it as Ashleisha. And we have a Barani radars. These are all low weight. Can be physically carried from one place to the other place. And these are all which is already deployed in the Indian Army by supplied by public sector units. And this is one of the weapon locating radar. So this radar is mainly used to locate or identify if there is any missile taking off, any rockets are mounted, or any slightly higher weapons lengthwise vertically mounted, they can be detected very easily. And I think this operates at 10 gigahertz because we supplied some components for this particular device in my earlier tenure. And this location, this is a WLR, they call it as a weapon locating radar. And this is my image. I am with our R&S global team in one of the meetings, and we were outside the country. And now let us talk about antenna basics. So already I have covered. Those things are theoretical. Here we have taken certain readings in our establishment. And this is about your Yagi-Uda antenna. This Yagi-Uda antenna has a reflector, radiating elements, and directors. This is a 8-element Yagi-Uda antenna. This is a 3D antenna, which is metal conducting pipes are there. And there is a dipole, folded dipole is connected, through which the signal is fed or it is received. So here we can see this is a pattern we have taken in our office. We have a small radiation pattern plotter developed by us. And we have taken a measurement for S-band and dipole antenna, where you almost got a figure of 8. There is some distortion. This is due to, because we don't have anechoic chamber in our place. So maybe due to some reflections, but the image is almost as good as taking measurements in a anechoic chamber. This is the radiation pattern plot, polar plot, 2-dimensional polar plot for 3dB. 3dB plot, you can see blue line. The actual power received is the red line. This is about our dipole E-plane antenna. So next is we have taken a measurement for patch antenna, which is made out of Rogers 5880 substrate. Is our own design, designed for 2.5 gigahertz. And the radiation pattern, you can see almost a shape of a apple, figure of apple. And you can see there is a 3dB power line. And there is a plot for 360 degrees. These are some examples which we have taken in our office. This is a H-plane for the same antenna. There is some slight backload. So whenever anybody is designing antenna, I think a lot of lectures are going to happen or happened already for designing antenna using simulation tools like HFSS, CST, FICO, REMCOM. We have a lot of companies, SEM1, computational electromagnetics. So like that, a lot of companies are supplying all these antenna simulation tools. The antenna simulation tools are basically to have, before you go fabricate and test it, this will be a simulation, whether your antenna will work or not in that particular design or shape. So those things can be viewed with the help of these electromagnetic simulation tools. And before you go for any antenna design, first you need to know what frequency you are going to design. Second, what is the bandwidth you are planning? Whether you want 100 megahertz or 500 megahertz, or you want ultra wide band, maybe from 3 to 10 gigahertz, first you decide. Then one more important thing is whether you should know whether the substrates are available. If you do all the design, you don't get the substrate, you are stuck. First ensure the raw material like high frequency laminates are made available. You have the appropriate connectors are available. And then you go for start designing any tool. Maybe you can use HFSS, SEM1, REMCOM, FICO, CST, And now there's nothing but how powerful is your tool, how fast you can simulate a result. So some tools may take some hours, some tools may take some days, some tools may take few minutes, but they give only a rough estimate whether your antenna will work or not. You can't get 100% realization by just simulating an antenna. So you take care of the impedance, what impedance you want, whether you want a 50 ohm impedance, on directivity. What is the directivity, expected directivity? How good gain you can get. And one more important is size of the antenna. Where you want to deploy this antenna. Suppose you want to deploy this antenna inside a mobile phone, you need to have a smaller design. Or you want to deploy the antenna on a spacecraft, you have to go for a bigger one. Or you need to mount the antenna on a vehicle, you have to go for a different. And next I told is the material. Next is testing facility. For any antenna to be tested, you need to have a VNA, vector network analyzer, so that you can test it comfortably. If not, you have to go for a test facility centers where you can pay charges and get your antenna tested. And material availability, please check for material. If you are designing any waveguide material, please ensure the particular type of waveguide is available, whether you want X-band, you want WR90, or you can go for any aluminum, or you can go for some other alloy metals. So ensure that you have the material, you have the design, and then you can go for final designing. So we have tested some of this is a small filter, which is hardly 1.8 centimeters, which works at 10 gigahertz. That this device is almost very small to the type of a SMA connector, only very small. Now people prefer to go for smaller ones because space constraint, your system will become smaller. So this is, we have another patch antenna in C-band. This is a transformer feed patch antenna made out of Rogers 5880 substrate. The dielectric constant of 3.2, a height of 0.8, and dielectric breakdown is somewhere around 10 gigahertz. Tan delta is 0.0001. So these are all certain parameters. Before we fabricate the antenna, we select. This is a patch antenna with transformer feed. And we have made some measurements in our office. It's a measurement of directivity and gain of a dipole antenna. So any gain measurements, you need to find the operating frequency. What antenna is designed, what is the bandwidth of that antenna, and where you will get the maximum performance of your designed antenna. After knowing the frequency, you can apply the Friis formulae. You can find what is the minimum distance you should place the order between a transmitter and a receiver so that your receiver gets plane wave instead of curved waves. Next is you have to find the transmitting power, what power you are going to feed to the system, and what is the power which will be received after all the transmission losses, line of sight obstacles, and all those things. So this is our basic setup where you have a signal source we can feed to the transmitter at keeping at a distance, meeting the Friis formulae, or more than that, you can feed the receiver to the power meter for simple power measurement, or you can connect to your vector network analyzer. This is a simple setup for college purpose. If you have a VNA, you can directly take the power from the VNA, feed to the transmitter. After the received power may please be, the received power may be fed to your measuring device. Again, you should know how good is your receiver sensitivity and how good is the phase noise of the carrier. All those things can be taken care. And we have the simple formula, gain equal to 4 pi s by lambda divided by square root of PR by PT, where C is the velocity of light, lambda equal to C by F, with which you can know the wavelength, and also the distance you can calculate 2D square by lambda, and power received, power transmitted. You can arrive at the gain of the antenna which you are using for receiving. Similarly, you can go for half power beamwidth measurements, and also in both planes, E plane and H plane, you can measure. So these are all the values which we have taken in our lab at 0 degree, 10 degree, 20 degree, towards right, towards left. These are manually we have taken, and we have an automated instrument which will plot 360 degree. But students can practice with this type of lab setup so that it can take some time for them to note down all the values and arrive at the gain of the given antenna and also directivity of the given antenna by applying the above formula. So this is an image about our testing facility where people are assembling boards, RF boards. We use some VCOs. We use some chips which are used to generate high frequency, other things. For any information or services, kindly contact us. We are on the website www.technilab.in, or you can mail me, or you can call me on my mobile. We also have an online store where we sell all these Raspberry Pi, Arduinos, BeagleBone. We also have some microcontroller ICs, etc. Any questions from any participants?
Ravikumar sir,
Yes, sir.
thank you for the wonderful session, sir.
Yes, sir.
One question asked by Vandana madam.
Yeah,
Where
please, sir.
RT duroid substrate in India? RT duroid substrate. It is in the chat box question.
Sir, RT Durite is manufactured by a company called Rogers Corporation.
1 second, sir. Vandana madam.
Hello.
Are you there?
Yes, sir.
Yes, ma'am. Please note it down, madam.
Madam. Hello.
Yes, sir.
Madam, Rogers Corporation is a US company.
Yeah, sir. Actually, the problem is when I have ordered the sample from.
Yeah.
Yeah, sir. I am aware of that. I have ordered the sample also from them.
Okay.
But it is very costly, and the shipping is also very costly.
No, please don't
So
pain yourself. Text
that's why
thing. We have.
I ask anywhere in
No,
India can we get other than FR4 substrate?
No, we have lot of stock. We import these items. Rogers also we have stock. We have Teconic substrates with us, which is equivalent to Rogers. It is called a TLY5.
Okay.
You can make a note of this number, TLY5. Dielectric 2.2.
Okay.
Height is 1.6 or 0.8 mm.
Hmm.
We also have TLC32 substrate. TLC32, which is a 3.2 dielectric. Height is 0.8, 1.6, 1.15. So you please mail me what your requirement. We have some stock. What is the
Okay,
size
sir.
you
Sure,
require,
sir.
ma'am? If
Yeah,
you require a smaller size, I can give free of cost.
Smaller size, sir. Smaller
What is the
size.
size? Can you specify?
No, actually, sir, currently I am working on one project.
Okay.
So during that, currently I'm working on FR4 only. But if I'm getting the hardware of that means PCB related to Rogers, then I will be checking the results with the Rogers also.
No.
So I will let you know once my simulation results done.
No, FR4 is a lossy material where the dielectric.
Yeah, that is the.
No,
Yes.
dielectric breakdown will be high when you go at high frequency.
Yeah, that's why.
See, regularly we supply these substrates to IITs. IIT Palakkad, they buy from us. Maybe tomorrow I'll be there in Palakkad tomorrow to supply these items. We have all RF accessories like high frequency connectors up to 40 gigahertz. Anything you require up to 40 gigahertz, we can supply all accessories, right from cable, connectors, substrates. And also we can help you in getting the antenna tested in anechoic chamber. Or if you want a plot, we have our equipment in the office. You can send the sample or you can come to Bangalore. You can get it tested.
Yes,
and
sir, sure.
You can go back.
Sure, sir.
And whatever.
Sir, one more question.
Yes, ma'am.
Hello.
Tell me, madam.
Sir, actually, at our institute, we are working on the in the field of RF and antennas. We are
Which is
giving
the
the projects to our students also, UG and PG students, based on
okay.
antennas, right?
Okay. Yes. Tell me, ma'am.
But we are not aware that how to utilize those products, whatever we have designed. Means filters are there, partial use, or maybe some kind of a application. Because what is happening, we are just fabricating the devices, we are testing it on VNA, and we are just showcasing it in our lab, frankly speaking.
No,
But
madam.
if we want, yeah.
In Bangalore, there are more than 400 companies who are working on wireless. Hello? Can you hear me? Hello?
Sir.
Yes, sir, we
There
can
are
hear.
there are 400 companies who are working on RF. Mostly all the items are imported. They are getting it imported from foreign countries. If you have any product, you can give it to us. We can refer to
Hmm.
those industries,
Okay.
or we will give the
Okay.
reference of those industries. You can approach them. They are also
Okay. Sure, sir.
looking badly to buy Indian product, which will be very less. By the way, what is
Okay.
the name of the institute, madam? You are working?
I'm from Somaya Vidyavihar University, KJ Somaya College of Engineering, Mumbai.
Mumbai, ma'am. Okay.
Yeah.
Actually, we also need some filters. What
Okay.
frequency have you developed it?
Sir, we have worked for 2.4 gigahertz
Mhm.
antennas, then 5.4 gigahertz antennas, and currently one of my group is working for the filter which is at 900 megahertz.
Madam, there is a huge demand for these type of items, but due to quality
Oh,
issues, nobody is
okay.
buying from India because finally it will affect their end product. So people are
Okay.
worried. So kindly do one
Okay.
thing. You go visit some websites. RFMW.
Yeah. Okay.
RFMW is a global website. There,
Acha. Yeah.
there you can launch your product. You
Acha. Okay.
there you can global platforms are there where
Okay.
all the new products are launched. But please ensure your
Okay, sir.
quality and repeatability is there.
Yeah. 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 Sure, sir.
If you make a filter, one filter or 10 filters, all 10 should have the same
Mhm.
test results.
Yes.
Not that one will work, one will not work.
Okay. Sure, sir.
Kindly use a high quality
Okay. Okay.
connectors, maybe from
Yeah.
Amphenol or
Yeah.
T connectivity or from any circuit. So use some good
Mm-hmm.
quality connectors which will give
Mm-hmm.
results and
Mm-hmm.
VSWR will be very less. You first qualify your product,
Okay.
then approach these companies who are
Okay.
buying. You can write to Bharat
Mm-hmm.
Electronics, they also buy a
Mm-hmm.
lot of filters. I'll give, you can note out my number in
Mm-hmm.
the previous slide or you can take from Go Source.
Yeah. Yeah. I have already taken your contact details.
Kindly contact me, I
Yeah.
can help you to some extent. And any other product
Yeah.
developed
Sure.
also, I
Thank you
can
so much.
inform you. And we are also developing a source,
Okay.
1 to
Sure.
12 gigahertz source we are developing. And we are developing on RF power meter
Okay.
also. Anything, it will be a low
Mm-hmm.
cost equipment as an import substitute. And we are also trying to launch it in the global
Mm-hmm.
platform for universities and other
Okay.
institutions. I can certainly help you to give some
Mm-hmm.
context where you can sell your product.
Yeah. Yeah. Surely, sir. I'll contact you. Yeah. Sure.
Very nice, madam, talking to you.
Yeah.
Yeah, yeah, please.
Thank you.
Any
Thank you so much. Yeah.
welcome, madam. Any other questions, sir?
No, sir, in the chat box, I've
I
seen.
see the chat box.
Yes, sir. Thank you, Ravikumar, sir.
Thank you, sir. Very kind of you. Thanks for giving this opportunity.
Yes, sir.
You can share the screen to the people, or
Yes,
I'll send you this presentation.
yes, sir.
Because very short notice, I could not go in detail. I did not make any equations and
A
other things
wonderful
because
session,
I know people will be bored. So
sir.
we have just covered from the top layer.
Yes, sir.
Thank you, sir. Yes, sir.
In the chat box,
Yeah.
uh,
Yes,
Agavan, who is professor in MIT Tiruchirappalli,
sir.
he has
NIT.
a rare
Yes.
illustration of unimaginable defense-oriented radar and rare costly equipments,
Okay.
instruments.
Okay.
It's a good feedback. I thank you, Ravikumar sir, on behalf of the ATAL Academy, the organizing institute, that is KLS Gokte Institute of Technology.
Yes,
Uh,
sir.
Sincerely, thank you for your time and this very informative session. Thank you so much, sir.
Thank you, sir. Have a good day, sir. Have
Good
a
day.
safe day and good health. Bye, sir.
Thank you, sir. Thank
Bye.
you. Yeah, thank you. Participants, we have next session. We start sharp at 2:30 p.m., which is on microwave applications in food processing industry by Professor Ramaswamy. Thank you. We'll break for. Thank you, sir. Thank you all once again.
Thank you, sir. Bye-bye.